Okay, now that we know the derivative of the quotient rule and the product rule, this is actually going to allow us to find the derivatives of all of our other trigonometric functions. Let me give you an example here of why, and all of this will be shown in the textbook. So if you want to see this, you can go in the textbook to see the proof of these. But I'll do, for instance, let's look at the derivative with respect to x of tangent x. Well, isn't that the same thing as the derivative with respect to x of tangent is sine of x over cosine of x? So if I was using the quotient rule, it'd be the low function, which is cosine of x, times the derivative of the high function, well, the derivative of sine is cosine of x, minus the high function, which is sine of x, times the derivative of the low function, derivative of cosine of x is negative sine of x. Okay, and this is all over the bottom function, which is cosine of x, quantity squared. Well, if we look at that, cosine of x times cosine of x is cosine squared of x. Negative sine x times negative sine x is plus sine squared of x. All of this is over cosine of x squared, which is cosine squared of x. That doesn't really matter, though. If you remember the trigonometric Pythagorean identities, cosine squared plus sine squared is just 1. So this is 1 over cosine squared of x, and 1 over cosine squared of x is the same thing as secant squared of x. So what did we just prove? We just proved that the derivative of tangent is secant squared, which is that exact rule that you see right here. The derivative of tangent x is secant squared of x. We could do the exact same thing for cotangent, looking at it as cosine over sine and finding the derivative. We could do the same thing with secant, looking at it as 1 over cosine, and we could do the same thing for cosecant, looking at it as 1 over sine of x, using the quotient rule for each one of those. When you use the quotient rule for each of those, you're going to get all of the following properties. The derivative of tangent is secant squared. The derivative of secant is secant tangent. What I'm going to do is highlight the other ones in a different color. The derivative of cotangent is negative cosecant squared, and the derivative of cosecant is negative cosecant cotangent. The derivative of the cos is a cofunction. The derivative of the normal function, secant and tangent, is the normal function, secant, right? Also, the derivative of cofunctions is negative, or are negative. So just like the derivative of sine is positive cosine, and the derivative of cosine, the derivative of a cofunction, is negative sine, the derivative of these cofunctions are also negative. So these are all rules you absolutely need to have memorized. Derivative of tangent is secant squared. Derivative of secant is secant tangent. Derivative of cotangent is negative cosecant squared. And the derivative of cosecant is negative cosecant cotangent. Not only would your Calc 1 teacher, who is me in this case, would expect you to memorize that, but also your Calc 2 teacher would. So in this class, because it's online, you are allowed a note card during the exam. If you were taking this class in person, you would not get a note card, and you would have to have every one of these rules memorized. That's what your Calc 2 teacher would expect. So I really, really want you to make sure that you memorize these rules, so you're successful not only in this class, but the next class. Okay, so let's use that to find the derivatives of the following functions. The first function is y equals x minus tangent of x. Well, not too bad here. We just need to find the derivative of each part. The derivative of x is 1. The derivative of tangent of x was secant squared of x. So what are we getting for the derivative of x minus tangent of x? Simply 1 minus secant squared of x. Let's look at the next problem. It says, find the derivative of x secant of x. Well, this is a product, isn't it? My first function being x, my second function being secant of x. So the first function is x. The derivative of the first function would be 1. The derivative of x is 1. The second function is secant of x. The derivative of the second function, the derivative of secant we just learned, is secant x tangent x. What are we using? It's a product, so we're going to use the product rule. The product rule says it's first times the derivative of the second plus the second times the derivative of the first, 1d2 plus 2d1. Our first function is x. The derivative of the second is secant x tangent x. The second function is secant x. And the derivative of the first function was 1. So I'm getting x, secant x, tangent x, plus secant x. And if you notice, both of those have a secant x involved in them, so I can factor out that secant of x. The first term, if you take out the secant x, x tangent of x would be left over. And the second term, if you divide it by secant x, just a 1 would be left over. So factoring it out, I'm getting the final answer of secant x times the quantity x tangent x plus 1. Okay, let's look at the next example. 9a, it says differentiate both forms of y equals 1 minus cosine of x all over sine of x. So what they're saying both forms of is they're saying, look, do it in the first form, which would be using the quotient rule, take the derivative exactly like it is. The second one is saying simplify first, and then you can deal with it that way. Okay, so let's look at this. In this case, we have the low function is sine of x, and we know the derivative of the low function, the derivative of sine of x, is cosine of x. The high function here is 1 minus cosine of x. And the derivative of the high function, well, the derivative of 1 is 0, and the derivative of negative cosine of x would be negative sine of x. Be really careful with your negatives and positives there, which turns into a positive sine of x. So if we do low d high minus high d low over what's below squared, again, y prime would be low d high minus high d low over what's below squared. We're using the quotient rule here. Low would be sine of x. D high would be another sine of x. Minus high, which would be 1 minus cosine of x, times the derivative of the high, which is cosine of x, all over the low function, which is sine of x, or sine squared of x, sine x squared, which is sine squared of x. Well, let's look at this and do some simplification. This is sine squared of x, and then this would be, if I distributed the cosine of x and the negative, so I'm doing 2 steps in one, I want you to be very careful with this. Cosine of x times a negative 1 would be minus cosine of x. And then I have to do a cosine x times a cosine x, but then I'm subtracting a negative, so that's actually going to turn into a positive, so it's going to be plus cosine squared of x. And all of this is over cosine squared of x. Now remember, when you have sine squared plus cosine squared, that equals 1. So what I'm getting on this one is 1 minus cosine of x all over cosine squared, or sorry, I don't know why I put cosine squared of x. That denominator was sine squared of x, right? So just being careful there. It's 1 minus cosine of x all over sine squared of x, which I could simplify or separate and write this a little bit differently. If I wrote this a little bit differently, totally depends on how you want to do it. This is the same thing as 1 over sine squared of x minus cosine of x over sine squared of x. And then 1 over sine squared of x would be cosecant squared of x. Cosine over sine is a cotangent. So that would be cotangent of x. And then we would have a 1 over sine x, which would be a secant of x. Okay? No, sorry, 1 over cosecant of x. 1 over sine of x is cosecant of x. So this is the other version of it, would be cosecant squared of x minus cotangent of x times cosecant of x. Okay, so I'm not going to lie. Where would have I stopped? I would have stopped right at this point right here. 1 minus cosine x over sine squared of x. Right, so that's the first way of doing it, is doing it literally just using the quotient rule. But what if, let me rewrite y here, y is 1 minus cosine of x all over sine of x. What if I separated and simplified this first? So this would be the same thing as 1 over sine of x. Let me clean that up real quick. 1 over sine of x minus cosine of x over sine of x. Well, 1 over sine of x is cosecant of x. And then cosine over sine of x is cotangent of x. And so if I wanted to find the derivative of this, I would find the derivative of cosecant, which is negative cosecant x cotangent x, minus the derivative of cotangent, which would be a plus, because it would be subtracting a negative, right? It would be minus negative cosecant squared, which would turn into plus cosecant squared of x. Now look at this, and that is the exact same thing as we got on the other one when we separated it and changed it into cofunctions. So these two things are mathematically equivalent, but depending on how you came at it, you would have gotten two look like very different answers. Mathematically, they're equivalent because the manipulation of your cofunctions, just writing them with your rational equivalencies. So I don't care which one of those answers you get, and the cool thing is neither does WebAssign. It would have given you credit for both of those answers. I don't know how you would have done this problem on the test. My guess is the majority of you would have just done the quotient rule. So I'll go ahead and put, you know what, why don't I put both answers down? And you pick and choose your answer. I don't care which one of them you got. Both of them would get credit as long as you showed work. Cosecant squared of x. There it is. Okay, now that I scroll and I actually look at the second part of this problem, what I realize is we already did this version of the problem right up here. So this was all done right up here. So what I would have said is, instead of, let me go back and erase my answers here, where I said or, I'm actually going to put my first answer is what we got doing it the first way, and then I'll put my second answer, which was negative cosecant x times cotangent x plus cosecant squared of x. I'm going to go ahead and put that in the second blank. And again, I'm not going to show that work because I did that work up there. And what this was just realizing that you could have taken the derivative of this trig function two different ways. One using the quotient rule, one separating, simplifying, using your rational identities for trig function, and then just straight up using the derivatives of the trig functions as you know them.